So let's recall what we need to do. Of course, we need to define a coordinate system first. So once that is done, we need to find the t, we need to find the u, and then we need to find the L minus L equal to T minus U. All right. So what is T? So which thing is moving? We only have one inertial, which is M. And then this M is moving. So there are two ways to calculate these kinetic energy. You can either calculate the linear velocity v of this mass and then use half mv squared, and then your v is theta dot times L. So you will have half ml squared theta dot squared. The other way to look at it is you can assume a rotation motion. So that's why your t equals to half j theta dot squared. So in this case, because it's rotation, your j is ml squared. So you can plug this in, you're going to have half ml squared theta dot squared. You can see no matter which method you pick, you should have the same kinetic energy, right? Depending on your the actual problem. So I won't say in this case, I don't know which one is better. I think they're all very relatively easy. But then in some cases, rotation might be better than linear. So just pay attention to that. So let's calculate the potential energy U. As I said, we need a reference. So which reference do you want to pick? Let's name these as O. The bottom point as A. And you can pick another point here as B. So which one do you want to use? 0.0? Yeah. Okay, 0.0. Okay, we have a lot of 0.0. All right, then, oh, we have a 1.8. Okay, I think I'll do both. Then you're going to see the difference. So actually, you can pick whatever point you want. O, A, B, or you can pick a C, D, whatever. So any of these points are going to work. It's just for your own convenience. Some of the reference point is going to give you easier solutions. So in this case, both O and A will be okay. I'm going to give you my solution right now. If you pick O as reference, then what is your U? You can open your mic or type it in the chat.
Wouldn't it be negative in relation to that datum point?
Yeah, it's actually negative, right? It's actually minus mg data edge. And then the data edge is the distance from your O point. So these length will be your data edge.
Is that based on the sign convention we talked about on the last lecture, or was that a certain direction? I don't remember. Why
So the negative, okay, so the negative here means smaller energy, relative reference. So because compared to the reference point O, at current location, let's name these as D. At current location D, your D location is actually lower than your O point. That means at this point, your potential energy should be lower. If the reference is 0, then that means the potential energy of D should be smaller than 0, right? So that should be a negative value.
Okay, yeah, I'm getting it now. Thanks.
So that means, okay, so what is data edge? Your data edge is just cosine theta L, right? So that's your U. And then after that, you calculate your Lagrangian equation, L equals T minus U. And then your T is half ml squared theta dot square minus mg cosine theta L. So as I said, in Newtonian method or Newton's method, the most common error is you have the wrong direction of force, or you have the wrong sign assigned to your force. In Lagrange's method, the error is usually from calculation. So for example, in this case, remember it's T minus U, you have another minus after that. So it's actually half ml squared theta dot square plus mg L cosine theta. All right, so you have these L, and then let's go back to see what is the conservative form of these Lagrange's method, okay? So the first one, you have to calculate d dt partial L partial changing rate. So in this case, that's theta dot. You have to pay attention here. Perhaps it's not clear. This is qi dot, which means it's the changing rate. And then the second partial derivative here is qi. That's your position. In this case, your changing rate is velocity. Okay? So that means you have to first calculate partial derivative with respect to velocity, and then calculate with respect to position. So let's talk about, well, that might be, let's give it, get it step by step. So let's first calculate the partial derivative. So in order to calculate that, you have to go back to your L expression, find your equation, and then find all the velocity terms. So the second one, the second term doesn't have velocity in it. You can assume there's a constant, it becomes 0. So the velocity only exists in the first term. So you have ml squared half, and then you take the 2 off, and then the theta 2 dot square becomes theta dot. And then there's ml squared theta dot. And then after that, you need to calculate one more time derivative with respect to these partial derivative. So ml squared, that's just constant or coefficient, and single dot becomes double dot. So I'm not sure if you're not from mechanical engineering, I'm not sure if you're familiar with the dot. So single dot means first order time derivative, and double dot means second time derivatives. Okay. So we are complete 50% of the work. So the other 50% is we have to calculate partial L over partial position. In this case, it's angular position. And then we go back to the L expression, find all the theta. So we just need to find theta, so we can assume theta dot is constant here. So, all right, so it becomes minus mg L sine theta. That's because d cosine theta, d theta equals to minus sine theta. All right? So 1, 2, we have this term, and then let's recall, we need to find d dt partial L partial theta dot minus partial L partial theta. So that is ml squared theta double dot minus mgl sine theta. That equal to 0. And then 2 negative becomes positive. You have ml squared theta double dot plus mgl sine theta equal to 0. So that's your final solution.